So here I'm going to introduce yet another method for deriving equations of motion for a mechanical system. And we start by defining the Lagrangian of our system, which we use the capital L to signify. And that Lagrangian is equal to T minus V, where T is the kinetic energy of our system, and V is the potential energy. And we use this Lagrangian in order to define the action of our system, which we define here, just going to call that A. And this action is equal to the integral of our Lagrangians from some initial time to some final time with respect to t. And it's true that for any physical system, mechanical, electrical, obviously here we're going to talk about mechanical systems, but the path that the object is going to take is the one that minimizes this action. And in fact, it can be shown that the minimum of this action, A, so of this integral here, is equal to the following. I'm going to write out the equation, and then I'm going to actually explain what all the terms are. It's equal to the time derivative, the partial derivative of our Lagrangian with respect to q dot I, plus the partial derivative of the Lagrangian with respect to qi. And that is equal to capital QI. And this equation right here is what's referred to as the Euler Lagrange equation. And this is the equation that we're going to use in order to derive equations of motion for our mechanical systems. So before we can actually use this equation in practice, we need to define a few things. Specifically, what is this lowercase q sub I and what's this uppercase q sub I? So the lowercase q indicates our generalized coordinates of our system. And in order to be a set of generalized coordinates, these coordinates must be minimal, complete, and independent. So minimal meaning that we don't have more coordinates than we need, so no redundant coordinates. Complete meaning that if you know these two coordinates, you can describe, say, where the position of any point on, say, a rigid body is in a plane. And independent means that one coordinate does not depend on the other, on any of the others. So I also like to think of these to, we can relate this to our degrees of freedom, right? So in order to be minimal, the number of generalized coordinates we have should equal our degrees of freedom and should describe those degrees of freedom. So for example, we've actually been using coordinates that can be used as generalized coordinates. So for example, when we have, say, a particle, so our pendulum here, right, and we use, say, a theta to describe our pendulum, the angle of this pendulum, we can actually use that as our generalized coordinate. So we can set, because in this case we have 1, because we have 1 degree of freedom, we can write q sub 1 is equal to theta, right? It's independent, but there's only 1. This is the minimal number, 1 degree of freedom, and it's complete. If you know that theta, you know where the particle is. Another example would be, maybe let's say we have a 2, so a double pendulum, right? And we have, say, theta 1, and we have theta 2. Well, we can write out, in this case, we have a 2-degree of freedom system, so we need 2 generalized coordinates. So we have, say, Q1 and Q2. Well, these can equal theta 1 and theta 2, right? Because again, if I know theta 1 and theta 2, I can always tell you where each of these particles are, and they're independent of one another. So really, we've been using coordinates that allow us, or that can be, to describe our system, that can be used as generalized coordinates. Now remember that you could, if you wanted to, you could say that you could describe the location of this point in terms of maybe an x1 and a y1, and this as x2 and y2. And you can quickly see that in this case you would have 4 coordinates, which does not meet the requirement of minimal. It's complete, but they're also not independent of one another, right? So these coordinates, so these x1, y1, x2, y2, would not meet the criteria. You could not use these generalized. This would not be a set of generalized coordinates. But like I said, we've actually been practicing for quite a while using or trying to identify coordinates that could easily be used as a set of generalized coordinates. And lastly, we have here a capital Q, I, which refers to generalized forces. And these are the forces that that are acting in the directions of the corresponding generalized coordinates. So for example, let's take this double pendulum here, right? So where we have theta 1 and theta 2. So if I have, say, again, Q1 is equal to theta 1 and Q2 is equal to theta 2, well then our Q1 is going to equal to this torque, right? So I'll call that torque 1. And then we have torque 2. Here. So again, you can think of it, these are the forces that are acting in the direction of the generalized coordinates. So now that we've defined what the Euler-Lagrange equation is, as well as the Lagrangian, let's discuss when we can use this equation and then how. So as for the when, you can use this equation for any mechanical system consisting of rigid bodies, and or particles. Okay, when you're calculating this with when you have rigid bodies in there, of course, it's going to affect how you calculate kinetic energy, because you have to keep into account not only translational but rotational kinetic energy, right? But other than that, the equations are the same no matter what your process is. You can use this for conservative and non-conservative systems, right? So again, conservative means only conservative forces, so gravitational forces and spring forces do work, right? And then non-conservative is when you have non-conservative forces that do work in the system. And a special case is that when you have a conservative system, you can actually just set your generalized forces, so your Q's sub i's are going to equal 0. And you can remember back to when we were using the conservation of energy, we had this requirement that we could only have a 1 degree of freedom system because we only ended up with one equation of motion, and you only could have one rigid body in there or particle, this requirement is not needed for using these equations. So, going back up to our first point here, I'll just write any number of rigid bodies or particles, and you can use this method. All right, and so next let's jump to the how. So the first thing that you should do is define your generalized coordinates. That's also whether they're generalized coordinates or just regular coordinates, and no matter what approach you're using to calculate your equations of motion, again, it's important to define what your coordinates, think about what the degrees of freedom of your system are, because that's going to ultimately tell you what number of equations of motion you need. So defining those generalized coordinates should always be your first step. Second thing you need to do is then define or calculate the Lagrangian, right? So this L equals T minus V. And then lastly, you're going to compute the Euler-Lagrange equation for each degree of freedom, or sorry, for each, I guess, yeah, it is for each degree of freedom, but for each generalized coordinate. Right, so you have this q sub I, oops, actually I was missing a subscript here too. You have these written in terms of I, and so I is the number, so I is equal to like the number or which generalized coordinate you have. So I'll put ith generalized coordinate. So if you have two generalized coordinates, you need to calculate this equation, this Euler-Lagrange equation, twice, right? And so this is a little bit different from the Newton methods, where basically you would get enough equations to account for the unknowns that you have, right? And then you kind of sum them all up. Here, you just calculate the Lagrangian, and then again, depending on the number of generalized coordinates you have, you then differentiate with respect to those different generalized coordinates, and how many coordinates you have is how many number of times you run this or calculate this equation. And so one other key step in this, in computing the Euler-Lagrange equation, is going to be the calculation of QI, these generalized forces, which again, if you come back to this comment here about conservative systems, this Q only pops up when you have non-conservative forces doing work. And so for this week, though, just to get our feet wet working with this Lagrange equation, this week we're going to assume that all of the systems that we're going to work with, all of our sample problems and homework problems, are going to deal with conservative systems where this Q is equal to 0. But in subsequent weeks, you'll see videos that are going to show you how to calculate this Q value. So for now, again, we're just going to assume that for the problems we're working with, Q sub I equals 0. And then once we're familiar with using this equation, practicing doing the partial differentiation and stuff, then we'll add on this additional component here, so this QI, right, which is going to result when you start to have, say, a force applied, external force applied to your system, or maybe you have a damper in there, or friction, or something like that.